Hello, this is Mr. Fawcett for part 2 of our lesson on defining continuity at a specific point. So we're actually going to jump down to, I believe, page 3. And we're just going to do some practice. Remember, in our last lesson, we talked about the 3 criteria for defining or for making sure a function is continuous at a given point, right? Number 1, our function had to be defined at that x value. Okay, so it couldn't be undefined, it had to exist. Number 2, the limit had to exist at that x value. And number 3, the value of the function has to equal the value of the limit at that x value. All right, so all 3 of those things have to be true, and we have to go through and prove all of those things if we're going to prove that a function is continuous. All right, if one of those things doesn't check out, we can stop and say the function's not continuous. So we're going to do one of these problems. We're going to do number 4. You guys can work on number 5 on your own, and then we'll do 1 out of the 2 from the next section as well. All right. Again, I encourage you to pause the video and try these problems on your own first, unless you really have no idea what to do. Again, you may figure out parts of it. You may be able to talk about 1 or 2 of the parts of the definition of continuity, but it's always better to struggle through something yourself before looking at the answer key and hearing the solution. Okay, so use the 3-part definition of continuity to determine if the functions below are continuous at the given points. For number 4, we are looking at the point x equals -2. So we have a piecewise function here, and piecewise functions are pretty popular in AP exam questions because you have to figure out which function to use for which limit and which function to use for the value of the function at a specific point. Number 1, I need to show that f of -2 exists. Okay, so I need to choose the correct piece of this piecewise function and substitute in -2 and see if it gives me a real number. I'm going to use the middle portion, right, because that is the function I'm supposed to use when x is equal to -2. So f of -2 is equal to 3 times -2 plus 2, which gives us -4. So that's the value of my function at -2. Part 1 checks out. The function is defined at -2. Now we need to figure out if the limit exists as x approaches -2. And if you think about what we need to prove to show that a limit exists, well, we need to prove that the 2 one-sided limits exist and are equal to one another. So the limit as x approaches -2 from the negative side of f of x is equal to the limit as x approaches -2 from the positive side of f of x. And then we need to figure out which f of x function we need to use. So on the left-hand side, right, when we're talking about the negative side, well, we're going to look at this piece because that's when x is less than -2. So we're going to look at -2 times the square root of x plus 6. And for my other side, as we approach -2 from the positive side, I'm going to be using this piece down here because that's when x is greater than -2. And that is e to the x plus cosine of pi times x. And now it's just a simple direct substitution. We don't have to do any manipulation because these functions are continuous at x equals 2. So if I substitute in I guess I should have a little arrow here, shouldn't I? Okay, so if I substitute in -2 over here, I get -2 times the square root of 4, because -2 plus 6 is 4, is equal to e to the -2 power plus cosine of -2 pi. This is going to simplify to -4. And the right-hand side is going to be 1 over e squared. Cosine of -2 pi is going to be the same thing as cosine of 2 pi, which is 1. So plus 1. And if you can't tell right away, these two quantities are not going to be equal to one another. 1 over e squared is never going to be a negative quantity. And it would have to be equal to -5 for those two sides to be equal. So it's never going to be. Which means this is false. And we can say not continuous at x equals -2. We should make sure to put, actually we don't have to put a not equal sign here as long as we say that this statement is false. And if you wanted to, not necessary, but you could say this shows, so limit as x approaches -2 of f of x, that does not exist. Okay, because the two one-sided limits do not exist, or sorry, the two one-sided limits are not equal, thus the limit is not going to exist, which means that we can't have a continuous function at x equals -2. Okay, it would be your task to go try number 5. However, we are going to move on to the second type of problem in this lesson. So I'm going to clear all this up. And we are going to look at number 6 down below. So it says, consider the function f of x to the right to answer the following questions. Part A, what two limits must be equal in order for f of x to be continuous at x equals -1? So again, when it says what two limits, they're talking about the one-sided limits, because the one-sided limits must be equal in order for the regular limit to be equal. So we need to figure out what are the two one-sided limits that must be equal for it to be continuous at x equals -1. Well, we have these two pieces of the piecewise function that are the pieces surrounding x equals -1. So the limit as x approaches -1 from the left, or the negative side of f of x, needs to be equal to the limit as x approaches -1 from the positive side of f of x. Now, this would not be an acceptable answer. This is too general. They would want to know what f of x are we talking about in these two, right? Which of these functions in the piecewise function represents which f of x? So for the left-hand side, we are looking at 2. Let me get out of here real quick. So 2 is the piece of the piecewise function that deals with values less than or equal to 1. And mx plus b is the function that deals with, or the piece of the function that deals with values, did I say mx plus b? Mx plus k. That piece of the piecewise function deals with values that are greater than -1 and less than 3. Because that would be our answer to part A. Now, if we look at part B, similar problem, it says, what two limits must be equal in order for f of x to be continuous at x equals 3? Well, we're going to have the limit as x approaches 3 from the negative side of f of x be equal to the limit as x approaches 3 from the positive side of f of x. And again, we need to figure out which f of x we're talking about here. So for the function that deals with values to the left of 3, that's our mx plus k. And the piece of the function that deals with values greater than 3 is -2. And again, you can just check that based on what it says right there. But in general, we're looking at these two functions for the red. The mx plus k is used for both because it is the piece of the function that is directly to the right of x equals -1 and directly to the left of x equals 3. This will be our answer to part B. Okay, part C says determine the values of m and k so that f of x is continuous everywhere. So if it's continuous everywhere, it has to be continuous at all points, and the 2 points that we need to check are the two pieces in the two x values where the function changes, right? It's a piecewise function and it changes at two different spots, -1 and +3. So to do that, we need to substitute into these limit equations to get rid of the limits, right? So if I use direct substitution, and I'll start with my first equation from part A. If I use direct substitution here, I'm going to get 2 for the left-hand side, because it's a constant function, so it doesn't matter what the x value is or what we're approaching, it's going to stay the same. And on the right-hand side, I get -m plus k. I just substituted in for my x. Okay, if I come over here for my red, I'm going to get 3m plus k is equal to -2. So you'll see here, by simplifying these limit equations, I've come up with two different equations that both have the values m and k. And if we think back all the way back to either pre-algebra or algebra 1, if I have a system of equations that has the same amount of variables as the number of equations, I should be able to solve it. And you could do this through elimination, you could do it through substitution. I am going to do it by, let's do it by substitution. That's the method I prefer. So I'm going to solve my blue equation for k. So I'm going to add m to both sides. So I get 2 plus m equals k. And I'm going to take this value right here and substitute it in for my k in my red equation. And I'm going to come up here and finish that. So I get 3m plus 2 plus m equals -2. And now I just have to solve for m. I get 4m plus 2 equals -2. 4m equals -4. M is equal to -1. If I know what m is, I can substitute back into one of my equations and find out what k is. I'm going to substitute into this one right here. So I have 2 minus 1 equals k, and I get k is equal to 1. So these two answers right here would be my answers to part C. Again, we're just using the parts of the definition of continuity. They're just asking this question in a little bit of a different way. Rather than just saying prove that the function is continuous, they're asking for pieces of that process by asking us what limits must be equal and throwing in some extra variables where we have to use some extra algebra to solve for their values. But it goes back to the same idea of what does it mean for a function to be continuous. All right, so you guys have one more to try down below. Similar type of problem, questions may be worded in slightly different ways, but again, it goes back to the same idea of becoming familiar with all three parts of the definition of continuity. So give that one a shot. Of course, write down any questions you have and be prepared to ask me them at a later date. All right, this is Mr. Fawcett. Have a great rest of your day.